solve one or two problems relating to one-dimensional steady-state heat conduction in cylindrical geometry, cylindrical wall, that is in a pipe of circular cross-section. And a very interesting related problem is the critical thickness of insulation. So let us solve one or two problems just to have its applications. What yesterday also we solved a problem, that is in the last class. Now this problem is like this. There is a cylindrical container The problem states like this. I am telling it, there is a cylindrical container, this is the axis, cylindrical container of radius r0, and the language of the problem is like that. Radioactive wastes are packed in a long thin walled cylindrical container. That means the radioactive wastes are packed, that means ultimately works as a solid cylinder type of thing. The radioactive wastes are packed in a long thin walled cylindrical container. The wastes generate thermal energy non-uniformly according to the relation that the volumetric energy generation rate at a point is given by Qg, Q0 into 1 minus R by R0 square, where Q0 and R0 are constants. Q0 and R0 are constant, that means it is varying with R, which means there is a cylinder solid, because this wall, this a container, thin wall container is packed with the radioactive waste, which generates energy in such a way. So what they want, obtain an expression for the total rate at which the energy is generated, total rate of energy generation, and use this result to obtain an expression for the surface temperature Ts. Surface temperature Ts, that means surface temperature Ts. So this is simplest again problem. First part is the total energy generation from the volumetric energy generation rate. So it is nothing but Qg is integral Qg dV. I usually represent volume as the V with a cut to distinguish it from velocity, where the convective heat transfer is associated with fluid mechanics, fluid flow we use V as the velocity, that's why I use the V. This V is the volume, dV is the small elemental volume. That means if we consider an elemental area like this in the container, thin cylindrical elemental area, at a radius r, and the thickness of this is dr, for example, then this will be nothing but Qg. What will be the area? What will be the volume? 2 pi RL into dr. And if you do that, you get the expression this as pi Q0 R0 square by 2. Very simple. You put this, 2 pi L will come to out. So R dr, R square by 2, that is R0 square by 2, because this now will be, this is for the entire volume. Now when I put it in terms of dr, it will be 0 to R0. So first term will be dr r dr, that is r0 square by 2, and second term will be r square by r0 square, r cube by r0 square dr. That means r0 4 and denominator r0 square, it will be again r0 square by 2. So ultimately you get pi q0 r0 square by 2. This thing I am not doing in the class. So this is the expression, there is nothing. But what is the Ts? Now to find Ts expression at this surface temperature, you have to apply certain intelligence, that always we don't want a routine boulevard, that we have to find out the temperature distribution, heat generation is not required. Simply the gross energy balance, the total heat which is being generated, or total thermal energy which is being generated, must go out from the surface, because the problem is prescribed by a heat transfer coefficient H and a T infinity. This problem is prescribed that the container is immersed in a liquid or fluid that provides a uniform convection coefficient H and at a temperature T infinity, and express Ts in terms of T infinity, H and Q0. So therefore, what we can write? We can write pi Q0 R square by 2 this is per unit length. So therefore, this has to be this. So this is Qg per unit length. I am sorry, the result I have written, since I have not worked it out here, that's why this mistake is there, that Qg by L is pi Q0 R0 square by 2. So this L is there, so L is come, so L will come out, so Qg by L. So the total Qg is this. This must be equal to H into outer surface area, which will be twice pi R0 into L into Ts minus T. So therefore, from here we get Ts. Ts will be equal to T infinity, that is the ambient temperature, plus pi will cancel. So 4 will be there, that means Q0 R0 by 4H pi R0 Q0 R0 square pi R0 Q0 R0 by 4H. I think it is okay. This is the problem.